We're Dexter Research, and for over 40 years, Thermopiles are what we do. Now, Thermopiles are generically defined as devices that convert thermal energy into electrical energy. That's true, and that's accurate, but it's also not very descriptive. So in today's clip, we'll take a quick look at what our Thermopiles are and how they work. Now, the building block behind a thermopile is a thermocouple. Many of you are familiar with thermocouples, where you have junctions of dissimilar materials, and when there's a temperature difference between those junctions, a small voltage is produced. That principle was discovered between metals by Thomas Seebeck back in the 1800s. And as you might expect, that's expanded to include materials of the silicon age today. Now connect any number of thermocouples in a series, and essentially you have a thermopile circuit, which produces a larger response based on the sum of all the individual thermocouples. With our thermopile materials, we simply miniaturize this series and arrange it such that the cold junctions are thermally tied to the perimeter of a substrate, and the hot junctions are suspended on a thin membrane in the center of the substrate. The arrangement of these hot junctions will define the sensor's active area. Electrically, like a thermocouple, the thermopile requires no external power to operate, only the temperature difference between the junctions to generate the voltage response. Also, the thermopile carries only the Johnson noise of the resistance, so it has the same noise as a resistor of equal value. To make the thermopile more sensitive and spectrally responsive, Dexter uses a special black energy-absorbing material right over the hot junctions on the membrane. Now, all objects above absolute zero radiate some form of electromagnetic energy. The filament from a light bulb, the broad energy from the sun, the wall behind me, even ourselves, we're all radiating some form of electromagnetic energy. And our black simply traps that radiated energy and converts it to heat, which is transferred directly to the hot junctions, increasing the temperature differential, therefore the sensitivity or the output of the sensor, without it having to actually touch the object that it's measuring. The resulting base thermopile is a fast, non-contact sensor with a voltage output that's directly proportional to the incoming radiation, and it's sensitive to a broad range of energy, from UV and visible to near, mid, and far infrared. Unlike a pyroelectric detector, the thermopile will generate no noise from microphonics or vibration, and unlike some other detector types, it can read a chopped or modulated signal as well as make continuous or DC measurements. One of the last considerations for the thermopile is to select a window or an optical filter to put in the thermopile cover. The cover will narrow the field of view mechanically, and the window or the filter will narrow down all that incoming energy to just the wavelengths of your interest. Our thermopiles are then hermetically sealed in robust transistor or TO packages, and with our various materials, they can operate at temperatures ranging from -55°C to some models that operate all the way up to 300 Celsius. That's our Thermopile 101. Keep in mind, we have over 30 different single and multi-channel models with dozens of window options and a set of encapsulation gases to help you tune the sensitivity and response time. We offer more configurations than all of our competitors combined. And with those options, we pride ourselves on our application support to help you select, customize, or even design the right fit for your sensing needs, whether it's one piece or a million. So call us or email us and take a look at our other videos for more information on model types and applications.